Somewhere in the Milky Way, worlds are racing around stars in hours, raining iron, drifting without suns, and hiding beneath strange, alien haze. Tonight, we'll gently explore the most bizarre exoplanets we've ever found, and what they reveal about how wild planet making can truly be. If you enjoy this journey, please like, subscribe, and comment where on Earth you're listening from, and whether you believe life may already exist out there in a form nothing like us. Before we can understand the strangest planets ever found, we have to begin with a stranger question than it first appears. How short can a year become before the word year stops feeling human? Here on Earth, a year is so deeply woven into our bodies and calendars that it feels almost natural, like the planet itself is breathing once around the sun every 365 days, carrying seasons, harvests, migrations, birthdays, memories, and the slow turning of winter into spring. Even Mercury, the fastest planet in our own solar system, still takes 88 Earth days to complete one orbit. And although that already seems swift compared with our own gentle path, it is still slow enough for the mind to follow. But once we leave the solar system and begin listening to the dimming of distant stars, the calm architecture we grew up with begins to fall away. Out there, around other suns, a year can last less than a day, less than a school afternoon, less than the time it takes a person to fall asleep and wake again. Some worlds circle their stars so quickly that if you could somehow stand above them and watch from a safe distance, you would not see the slow dignity of an orbit. You would see a glowing bead racing around a flame, pulled so near to destruction that its entire existence becomes a negotiation between gravity, heat, and time. The first reason we know so many of these short-year planets is not because they are necessarily the most common kind in the galaxy, but because they are among the easiest for us to catch. The universe does not hand us planets directly. It gives us shadows. Most exoplanets are discovered by the transit method, where a telescope watches a star and waits for the faintest, most disciplined interruption in its light. If a planet passes in front of its star from our point of view, the star dims by a tiny amount, sometimes less than 1%, sometimes far less. And if that dimming happens again and again at regular intervals, astronomers begin to suspect that an unseen world is crossing the star's face. A planet with an orbit like Earth's may transit only once a year, so confirmation takes patience, repetition, and luck. But a planet that circles in 2 days, 1 day, or only a few hours announces itself over and over like a soft metronome hidden in starlight. This observational bias matters because science is not only about what exists, it is also about what our instruments are most able to notice. The shortest years are overrepresented in our catalogs because they are easier to confirm, and yet that does not make them less real or less astonishing. They are real worlds living at the innermost edge of planetary possibility, and they reveal what happens when orbital mechanics is pushed into a narrow, almost violent corner of nature. The underlying mathematics begins with an old and beautiful relationship. Kepler's third law, refined by Newton, tells us that the orbital period of a small body depends mainly on the distance from the central mass and the mass of that central object. In its familiar form, the square of the orbital period is proportional to the cube of the orbital distance. So if a planet moves much closer to its star, the period collapses quickly. Halve the orbital distance, and the year does not merely become half as long, it becomes dramatically shorter. This is why a planet skimming close to a small red dwarf can finish an orbit in hours. It is not magic, and it is not an exception to gravity. It is gravity doing exactly what gravity must do, pulling the planet inward while the planet moves sideways fast enough to keep missing the star. An orbit is not peaceful because nothing is falling. An orbit is peaceful because the falling never quite ends. For an ultra-short period planet, that falling is steep, fast, and extremely close to the furnace of the star. K2137b is one of the most striking examples. An Earth-sized planet around a small M dwarf with an orbital period of about 4.3 hours, meaning its year is shorter than many people's evening routine. Imagine beginning a night on such a world and knowing, if words like night and year still had any meaning there, that the planet would complete an entire revolution before midnight had fully settled on Earth. But the number alone is only the doorway. The deeper strangeness is what such a short orbit implies. A planet so close to its star is likely exposed to extreme stellar radiation, intense tidal forces, and surface temperatures that may erase any familiar idea of land, weather, or atmosphere. If it is rocky, its day side may be molten or stripped bare. If it once had volatile compounds, much of them may have escaped long ago. If it began as a more ordinary planet farther out, its present orbit might be the last stage of a long inward migration, shaped by tidal interactions, gravitational nudges, or earlier instability in the system. Scientists do not treat these possibilities as simple stories with one guaranteed ending. They model them as competing pathways, each depending on mass, density, stellar age, internal composition, orbital eccentricity, and the efficiency with which tidal energy is dissipated inside the planet and star. The closer a planet comes, the more the star's gravity pulls unevenly across its body. The near side feels a stronger tug than the far side, and that difference creates tides. Not just ocean tides like those on Earth, but tides in rock, mantle, crust, and perhaps the entire planetary shape. Over time, these tides can drain orbital energy, circularize the orbit, lock the planet's rotation, and in some cases, slowly pull the planet inward. Tidal locking is especially important for these worlds. On Earth, the sun rises and sets because our planet rotates freely relative to its orbit. But a close-in planet may become synchronized, always showing one hemisphere to the star and one hemisphere to space, creating a permanent day side and a permanent night side. On a world with a year of only a few hours, the language of morning and evening becomes almost broken. The star may hang fixed in one part of the sky, enormous and merciless, while the opposite hemisphere rests under endless dark. Not cold in any ordinary sense, perhaps, but cooler than the illuminated face. Between them lies the terminator, the twilight boundary, a ring of transition where winds, heat, chemistry, and radiation may meet in ways we cannot fully reconstruct without models. The geometry is simple enough to draw, but the physics quickly becomes rich. Heat transport by atmosphere if one survives. Magma circulation if the surface is molten. Magnetic interactions with the stellar wind, and possible mass loss into space. Some ultra-short period rocky planets may resemble evaporating embers, not because they burn like wood, but because their surfaces can reach temperatures where minerals vaporize, creating a thin rock vapor atmosphere that may condense on the cooler side or escape altogether. Others may be dense, iron-rich bodies, perhaps stripped of lighter silicates by impacts or by long exposure to stellar heating. Though each case must be studied carefully before turning possibility into conclusion. K2-141b, with a period of roughly a third of an Earth day, offers another window into this class of worlds, often discussed as a possible lava planet, where silicate rock may behave almost like a volatile substance under extreme heat. On such planets, the old categories of geology and weather begin to merge. A cloud may not be made of water. A vapor may come from stone. A surface may not be a stable floor, but a glowing ocean of molten minerals, and the planet's orbit, rather than being a quiet path through space, becomes the engine that keeps the entire world in an exotic physical state. Yet, it is important to move slowly here, because exoplanet science is built from indirect evidence. We often know the radius from the transit depth, the orbital period from repeated dips in starlight, and sometimes the mass from radial velocity measurements, where the star wobbles slightly under the planet's gravitational pull. From mass and radius, we infer density. And from density, we begin to constrain composition. But a density is not a photograph. A light curve is not a landscape. Between the data and the imagined world lies a field of models, each one shaped by assumptions about interior structure, atmospheric escape, stellar activity, and formation history. This is what makes these short-year planets so valuable. They are not merely bizarre objects for wonder. They are laboratories for testing how far planetary materials can be pushed before they lose atmospheres, melt surfaces, decay orbits, or cross into destruction. There is also a historical irony here. For centuries, the solar system gave us a tidy sample. Small rocky planets inside, gas giants outside, icy bodies farther still. That arrangement encouraged a quiet expectation that planets formed where we see them now. But the discovery of close-in giants in the 1990s, followed by super-Earths and ultra-short period planets, forced astronomers to accept that planetary systems evolve. Planets migrate through disks of gas and dust. They scatter one another. Their orbits shrink under tides. They may be born in one place and die in another. A year lasting only hours is therefore not just a number. It is a fossil of motion, a clue that the system has a past. Perhaps the planet formed farther out and spiraled inward. Perhaps it is the surviving core of something once larger. Perhaps it formed close to the star after the inner disk evolved in a particular way. Different systems may have different answers, and the truth may be less like a single explanation than a family of possible histories. Near the innermost boundary, another question waits quietly. How close is too close? The Roche limit describes the distance inside which tidal forces can tear apart an object held together mostly by self-gravity. Though real planets with material strength, layered interiors, and complex histories do not always behave like simple, fluid bodies. Atmospheric drag can also matter if a planet orbits so close that it skims through extended stellar material. Stellar magnetic fields, radiation pressure, and high-energy particles may help sculpt whatever gas remains. In this region, a planet is not simply orbiting. It is being processed. Its star is not only a source of light, but an environment, a furnace, a sculptor, and eventually, perhaps, an executioner. And still, for now, these planets endure. They keep circling. Every few hours, another year passes. Every transit writes the same brief shadow across a distant star. And that shadow crosses our detectors after traveling for years through the dark. There is something deeply calm in that thought, even when the worlds themselves are violent. We are not watching them directly. We are reading their rhythms. A star dims, brightens, dims again, and from that small pulse, we infer an entire planet racing around a sun beyond our own. The shortest year exoplanets are bizarre because they compress celestial time into human time. They take something that should feel vast and slow, the orbit of a world, and fold it into a single evening. They remind us that a year is not a sacred unit of nature, only the measure our planet happened to give us. Somewhere in the Milky Way, while you listen in the quiet dark, a rocky world may be completing its second orbit of the night, then its third, then its fourth, silently counting years in hours beside the face of a small red star. And in that almost impossible speed, the universe whispers the first lesson of strange planets. Even time itself feels different when the world beneath it is built too close to the fire. If the shortest year planets teach us that time can be compressed until an entire orbit fits inside a single evening, then planets with more than one sun teach us something quieter and perhaps even more disorienting, that the sky itself does not have to be simple. We are born under one star, and because the sun rises alone, crosses the day alone, and sinks alone beyond the horizon, the human mind tends to imagine a planetary system as a clean arrangement, one central fire with worlds circling around it like beads on invisible rings. But the galaxy is not obligated to preserve the habits of Earth. Many stars do not live alone. They are born in pairs, triplets, and larger families, emerging from the same collapsing clouds of gas and dust, bound together by gravity before any planet has had time to cool. And in those systems, the question becomes beautifully complicated. Where can a planet move when the center of light is not one object, but two, or three, or more? The simplest case is a binary star system, two stars orbiting their shared center of mass, called the barycenter, a point that may lie between them if their masses are similar, or deep inside the larger star if one dominates the other. From far away, the pair may look like a single glimmer, but dynamically, it is a dance of two gravities, two radiation fields, two winds, two histories. A planet in such a system has several possible arrangements. It may orbit one star while the second star stays far away. A configuration often called an S-type orbit, where the planet's immediate life is shaped mostly by one sun, while another distant sun becomes a bright wanderer in the sky. Or it may orbit both stars together in a P-type or circumbinary orbit, tracing a wider path around the entire pair, as if the two stars together form one luminous heart. The mathematics behind this is not merely poetic, it is one of the old, difficult problems of celestial mechanics. Two bodies under gravity can be described with elegant precision, their paths predictable through conic sections and conservation laws. But three bodies introduce a deeper kind of complexity, because every object pulls on every other object at once, and the system no longer has a single simple solution that works for all cases. This is why planets around binary stars were once treated with caution in theory. If the planet is too close to the moving stars, the changing gravitational tugs can stretch its orbit, pump up its eccentricity, or eventually throw it away. If it is far enough out, the rapid motion of the inner binary can blur into a more stable combined gravitational source, not perfectly smooth, but smooth enough for a planet to survive across millions or billions of years. Numerical simulations, which follow gravitational interactions step by step through time, show that stable circumbinary planets generally need to orbit at several times the separation of the two stars, with the exact boundary depending on the star's masses, their orbital eccentricity, and the tilt of the planet's path. The boundary is not a wall painted in space. It is a region where order gradually gives way to chaos, where a slightly different starting position can mean the difference between a world that remains and a world that is expelled. When NASA's Kepler mission found Kepler 16b, the discovery felt like a quiet crossing of that boundary between speculation and observation. Here was a real circumbinary planet, a Saturn-sized world orbiting two stars roughly 200 light-years away, and because it passed in front of its stars from our point of view, the telescope could measure the delicate rhythm of eclipses and transits in a system far more intricate than a single star with one planet. Kepler 16b became famous because it reminded people of fictional double sunset worlds. But scientifically, its importance was not that it looked like a movie. It proved that planets can exist in stable orbits around two moving suns. And it gave astronomers a real system where the geometry of eclipsing binaries, planetary transits, stellar masses, orbital inclinations, and timing variations could all be woven together into a precise physical model. In a circumbinary system, transits do not behave with the clean regularity of a planet crossing one star at the same interval every time. The stars are moving too, so the planet may transit one star, then the other, then miss a transit from our viewpoint, and the spacing can vary in ways that would look confusing unless the whole gravitational clockwork is understood. This makes the detection harder, but it also makes the reward richer, because every irregularity carries information. The moving shadows become measurements of mass, radius, alignment, and orbital architecture. Later systems, such as Kepler 47, revealed that circumbinary planets do not have to come alone. Multiple planets can orbit a pair of stars, showing that planet formation around binaries is not merely possible as a rare accident, but can produce organized systems with more than one surviving world. That raises a deeper question about birth. Planets form in disks, flattened structures of gas and dust left over from star formation. Around a single young star, the disk can settle into a rotating plane where dust grains collide, stick, grow into pebbles, planetesimals, embryos, and eventually planets. Around two stars, the inner disk is stirred by the binary's gravity. Spiral waves can ripple through the gas. Dust can be trapped, scattered, or concentrated. The inner region may be cleared out, leaving a central cavity, while material farther out remains stable enough to build planets. Some models suggest that circumbinary planets may form farther from the stars and migrate inward until they reach the edge of the unstable zone, where the disk's structure and gravitational resonances slow or halt their motion. This may help explain why several known circumbinary planets are found near the inner stability boundary, as if they drifted inward through the disk and came to rest at the closest safe distance. Yet, this is still an active field, and the exact pathway may differ from system to system. A planet around two suns is therefore not just a finished object. It is a clue preserved from a turbulent childhood, a fossil of disk physics written in orbit. Now, imagine standing not on Kepler-16b itself, because it is a gas giant without a solid surface like Earth, but on a hypothetical moon or rocky circumbinary planet in a similar system. The sky would not follow the calm pattern our ancestors used to build calendars. Sometimes, the two suns would rise close together, one larger and warmer, one smaller and redder, their disks drifting relative to each other day by day. Sometimes, one star would eclipse the other, dimming the daylight in a way no ordinary cloud could explain. Shadows might double, separate, overlap, and merge. Seasons could depend not only on the tilt and orbit of the planet, but on the changing arrangement of two stars around their barycenter. If the planet were in the habitable zone, that zone itself would be a time-averaged region, shaped by the combined luminosity of both stars, and in eccentric binary systems, the incoming energy could vary in subtle or dramatic rhythms. Habitability in such places is not impossible, but it becomes a calculation with more moving parts. Stellar luminosities, flare activity, orbital stability, atmospheric heat transport, planetary rotation, cloud feedback, and long-term climate buffering. If one star is a quiet orange dwarf and the other a smaller red dwarf, a planet may receive a relatively gentle combined light. If one star is massive and short-lived, the system's lifetime may be too brief for stable biological evolution as we understand it. If the stars are close together, the planet may orbit both from a safe distance. If they are widely separated, planets may instead form around each star separately, each world living under one main sun, while the other star shines as a brilliant seasonal visitor. In triples and higher-order systems, stability usually depends on hierarchy. Two stars may form a close binary, while a third orbits far away, so the system behaves like nested orbits rather than a chaotic three-way scramble. Add more stars, and the same principle often appears. Binaries within binaries, pairs orbiting pairs, each level separated enough to reduce destructive close encounters. A planet in such a system might orbit one star, one pair, or, in a more distant mathematical possibility, the combined mass of several stars. Though the farther out it goes, the weaker and colder those suns may appear. A world with many suns would not necessarily be flooded with many days. If the stars are distant enough for stability, some may be little more than bright points, beautiful but not warm, companions in the night rather than true suns of the day. This is where the phrase "planet with many suns" becomes more subtle than it sounds. It is not only a visual wonder, it is a statement about gravitational architecture. The planet's sky tells a story of how stars grouped themselves at birth, how unstable young systems expelled some members and kept others, how disks survived or reformed around moving centers of mass, and how tiny grains of dust managed to grow in a place where the gravitational floor was never still. In that sense, these worlds are bizarre, not because they break physics, but because they obey physics in arrangements our solar system never taught us to expect. They remind us that Earth's one-sun sky is not the universal template, only our local version of order. Elsewhere, a day may be lit by 2 fires. A year may be measured around a moving pair, and twilight may arrive not all at once, but in layers, as one star sets while another lingers pale above the horizon. And somewhere in the deep catalogue of worlds still waiting beyond our instruments, there may be a planet whose inhabitants, if anything ever looked up from its surface, would not ask why there are 2 suns in the sky. They would find it ordinary. They would build their myths, their measurements, and their sense of time around a double light. And perhaps that is the quietest lesson of all. The bizarre is often only the familiar seen from another world. Some of the strangest planets in the galaxy are strange not because they burn, or freeze, or rain metal, or circle 2 suns in a sky filled with doubled shadows, but because they have no sun at all. No sunrise to measure their mornings, no parent star to hold them in a familiar orbit, no warm center around which their years can be counted, only the immense quiet between stars, where a world can drift through the Milky Way like a dark ship with no harbor. These are rogue planets, or free-floating planets, planetary mass bodies moving through the galaxy without being gravitationally bound to any star. And the first thing that makes them so unsettling is how directly they challenge the emotional definition most of us carry in our minds. We tend to imagine a planet as something that belongs to a system, something that circles a star, something whose identity is partly given by the light it receives. But gravity does not require every planet to keep its birthplace. A world can be born in a disk around a young star and later be thrown out, or perhaps form in isolation from a collapsing pocket of gas too small to ignite as a star. And in either case, it becomes a kind of orphan object, not dead in a simple sense, but removed from the central rhythm that makes planets feel ordinary to us. The ejection pathway begins in the restless childhood of planetary systems, when the disk of gas and dust is still settling, when protoplanets are growing, when giant worlds migrate through the disk, and when close gravitational encounters can trade energy with brutal efficiency. In Newtonian mechanics, if two planets pass near each other, their mutual gravity can alter both orbits, and in a crowded young system, the smallest change can become decisive. One planet may move inward, another outward, and a third may gain enough orbital energy to exceed the escape velocity of the star entirely. Escape velocity is not a poetic phrase. It is the speed required to break free of a gravitational well, and if repeated encounters push a young planet above that threshold, the star does not call it back. It leaves on a hyperbolic or loosely unbound trajectory, carrying with it whatever atmosphere, moons, heat, and scars it had at the moment of exile. In dense star-forming regions, passing stars can also disturb wide orbits, and because young systems are often born near other young systems, a planet far from its host star may be especially vulnerable to being stripped away. There is another possibility, quieter and harder to classify, in which a rogue planet forms more like a tiny star from the direct collapse of a fragment of molecular cloud, but never reaches enough mass to become a brown dwarf or ignite sustained fusion. This route blurs the boundary between planet and failed star, and scientists are careful here because mass alone does not always tell the full story of formation. Some objects below the deuterium burning limit may form like stars, while some massive planets may form in disks. So the word planet becomes not only a label of size, but a question about origin, environment, and history. The deepest difficulty is that rogue planets are almost invisible. A normal exoplanet often reveals itself by interacting with its star, dimming the starlight when it transits, tugging the star so it wobbles through radial velocity, or reflecting and emitting light close enough to a star that we can infer its presence. A rogue planet has no such bright companion. If it is old and cold, it emits almost no visible light. If it is small, it may be darker than the background night itself. Yet even a dark planet has mass, and mass bends space-time. And this is where one of the most delicate tools in astronomy enters the story: gravitational microlensing. When a rogue planet passes almost perfectly in front of a distant background star, its gravity slightly warps the path of that star's light, making the background star appear temporarily brighter. No one sees the planet directly. Instead, astronomers watch the star brighten and fade in a smooth, characteristic curve, a brief swelling of light caused by an unseen object crossing the line of sight. The scale of that brightening depends on alignment, mass, relative motion, and distance, and the duration of the event can give clues about the lensing object. A stellar lens may produce an event lasting weeks. A planetary mass lens may create a much shorter signal, sometimes lasting only days or even hours. This is both the promise and the frustration of microlensing. It can reveal objects that emit little or no light, including free-floating planets. But the events are rare, unrepeatable, and dependent on chance alignments across enormous distances. Once the lens has passed, the brightening is gone, and the same exact event will not happen again. Astronomers therefore need to monitor huge numbers of stars, especially toward the crowded central regions of the Milky Way, where background stars are dense enough that alignments become more likely. The Nancy Grace Roman Space Telescope is expected to transform this search because a wide field of view and infrared sensitivity can watch enormous star fields with the patience and precision needed to catch these brief gravitational flickers. Ground-based surveys have already found candidates, but Roman may help turn scattered hints into population statistics, allowing scientists to ask not just whether rogue planets exist, but how many there are, what masses they tend to have, and whether their distribution points more strongly toward ejection from planetary systems or formation in isolation. The number matters because it touches the history of planetary systems everywhere. If rogue planets are extremely abundant, then planet formation may be far more violent and inefficient than a calm solar system diagram suggests. Every free-floating world may be evidence that young systems shed material, that planets compete gravitationally, and that stability is often achieved by loss. Yet a rogue planet is not necessarily a frozen stone without inner life. Without a nearby star, its surface receives no sunlight, so photosynthesis as we know it would not be available, and any exposed surface would likely become extremely cold over time. But planets are not heated only from the outside. They also carry internal heat from formation, radioactive decay, tidal histories if they once had moons or close encounters, and in some cases, residual warmth trapped beneath insulating layers. A thick, hydrogen-rich atmosphere, in theoretical models, could act as a powerful blanket, trapping internal heat through collision-induced absorption and possibly allowing liquid water beneath certain conditions, though such scenarios depend on mass, atmosphere retention, chemistry, age, and pressure, and should be treated as possibilities rather than claims. A rogue planet with a deep ocean beneath an ice shell might resemble the icy moons of our own outer solar system in one respect. It could hide warmth below darkness. On Earth, life exists near hydrothermal vents without sunlight, supported by chemical energy from the planet's interior. So astrobiologists sometimes consider whether a free-floating world with water, rock, and geochemical gradients might host environments where chemistry remains active. This does not mean rogue planets are likely living worlds, and it certainly does not mean we have found life on one. It means only that the absence of a star does not automatically erase every form of planetary complexity. Some may be gas giants, drifting silently with faint infrared glows. Some may be rocky bodies, stripped bare and frozen. Some may carry moons, though retaining moons after ejection would depend on the violence of the encounter and the stability of the moon's orbit. Some may have been thrown from systems like ours, implying that the early solar system may also have lost bodies we will never see again. The emotional power of rogue planets comes from this combination of darkness and hidden structure. They are invisible until gravity betrays them. They have no year in the usual sense, because there is no star to orbit, yet they still move around the galaxy, following paths shaped by the Milky Way's total gravitational field. Their seasons, if the word can be used at all, are not set by sunlight, but by cooling interiors, changing atmospheres, and the slow passage through interstellar space. A rogue planet turns the idea of planetary identity inside out. It asks whether a world is defined by what it circles or by what it is. And as we drift through this chapter of strange planets, the answer becomes more spacious. A planet can be a member of a bright family, or it can be a solitary traveler. It can be warmed by a star or sealed within its own fading heat. It can be found by shadow, wobble, image, or by the quiet bending of light around something no eye can see. Somewhere, perhaps in the dark lanes between the spiral arms, countless worlds may be moving without dawn, without constellations fixed in the same way ours are, without any local sun to call home. And their existence reminds us that the galaxy is not only a place of shining things, it is also a place where dark worlds travel silently, carrying the memory of formation, exile, and gravity through the long night between the stars. There are planets that seem strange because of where they move, and planets that seem strange because of what fills their skies. But WASP 76b belongs to a more unsettling class of worlds, where even the idea of weather has been transformed into something almost mineral, almost industrial, almost impossible to imagine without first letting go of Earth. On our planet, rain is a soft return of water from sky to ground, a cycle shaped by oceans, clouds, sunlight, pressure, and gravity. And because we have lived beneath that cycle for all of human history, the word rain carries a quiet familiarity, something silver on windows, something that feeds forests, something that cools the air before sleep. But on WASP 76b, the physics is not written in water. It is written in heat, metal, radiation, and violent atmospheric motion. This world is an ultra-hot gas giant orbiting an F-type star far from our solar system. And it travels so close to that star that a full year there lasts only about 1.8 Earth days. Its orbital distance is only a small fraction of the distance between Earth and the Sun, so close that the planet is not merely warmed by its star, but overwhelmed by it, irradiated with an intensity that pushes the atmosphere into chemical regimes we do not experience anywhere in the solar system. Because WASP 76b orbits so tightly, it is widely expected to be tidally locked, meaning the same hemisphere faces the star all the time, while the opposite hemisphere faces away into permanent night. Tidal locking is not a mysterious exception. It is the natural outcome of repeated gravitational distortion, where the star raises tides in the planet's gaseous envelope and, over time, dissipates rotational energy until the spin period matches the orbital period. The result is a planet divided not by seasons or continents, but by a permanent geometry of light. One side bathed endlessly in stellar fire, the other held in a darkness that is still extremely hot by earthly standards, but cool enough for a different kind of chemistry to begin. On the day side, temperatures can climb high enough that substances we know as solid metals may enter the atmosphere as vapor. Iron, which on Earth lives inside bridges, blood, tools, rocks, and planetary cores, can become part of the air. That is the first deep rupture in intuition. The air of a planet does not have to be made of gentle gases alone. Under enough heat, Even refractory elements can become atmospheric participants. When starlight passes through the thin outer limb of WASP 76b during transit, some wavelengths are absorbed by atoms and molecules in the atmosphere, leaving fingerprints in the spectrum. This technique, transmission spectroscopy, is one of the great quiet arts of exoplanet science. Astronomers do not scoop the air. They do not fly through the clouds. They read what the atmosphere removes from starlight. High-resolution instruments can separate spectral lines so finely that motion itself becomes visible through Doppler shifts, allowing scientists to infer not only what is present, but how the gas may be moving. In the case of WASP 76b, observations revealed an intriguing asymmetry in iron absorption, with strong evidence for iron vapor near one side of the terminator and a weaker or absent signal where cooler atmospheric flow might allow iron to condense. The terminator is the borderland between day and night, not a sharp wall, but a planetary twilight ring where air from the burning hemisphere is carried toward darkness. If winds move vaporized iron from the day side into cooler regions, the iron may transition from gas into liquid droplets or condensates, falling deeper into the atmosphere in what we describe carefully but vividly as iron rain. It is not rain in the way we know it. There is no meadow below, no roof, no human listener in a quiet room. WASP 76b is a gas giant, so there may be no solid surface where drops could gather. Instead, the rain may fall through layers of atmosphere, sinking into hotter depths, becoming part of a global circulation system that is more like a furnace wrapped around a planet than a weather map. The real marvel is not simply that iron can rain. It is that the planet has become a three-dimensional chemical engine where temperature, wind, rotation, gravity, and radiation separate the atmosphere into regions with different compositions. On Earth, weather is often explained through pressure gradients, evaporation, condensation, latent heat, and the Coriolis effect. On an ultra-hot Jupiter, those ideas do not disappear, but they are joined by thermal dissociation, ionization, radiative transfer, opacity, cloud microphysics, and chemical equilibrium that may fail because winds move material faster than reactions can restore balance. The day side is so strongly heated that molecules can break apart and atoms can remain in forms that would normally be locked into condensates or clouds on cooler planets. The night side, though still incandescent by ordinary standards, acts as a relative cold trap, a place where some species may condense and vanish from the observable upper atmosphere. This day-night contrast creates a planetary circulation problem of extraordinary complexity. Models suggest that hot Jupiters often develop powerful winds, sometimes including eastward equatorial jets that transport heat around the planet. But with WASP 76b, the stakes of that heat transport are chemical as well as thermal. A parcel of gas does not merely warm or cool. It may change what it is able to contain. Iron can exist as vapor in one longitude and as condensate in another. The same element can be visible to a telescope on one limb and hidden on the other, not because it has ceased to exist, but because the local physics has changed its form. This is why WASP 76b matters beyond its headline. It demonstrates that exoplanet atmospheres cannot always be treated as one-dimensional blankets. For many years, when data were sparse, scientists often modeled planetary atmospheres as average columns, simplified layers of pressure and temperature stacked above a world. That approach is powerful, but ultra-hot Jupiters force a more advanced view. Their atmospheres are uneven in longitude and latitude. Their morning and evening limbs can differ. Their spectra can change depending on orbital phase. Their winds can imprint velocity patterns into spectral lines. Their chemistry may be local, asymmetric, and time-dependent. The planet becomes not a sphere with one temperature, but a moving climate machine, observed through fragments of light. There is a strange gentleness in how we know this violent place. A tiny dimming of a star, a thin rim of atmosphere, a few missing wavelengths, a shift in spectral lines, and from that, a picture forms. A world larger than Jupiter, circling its star in less than 2 days. One face blazing, one face dark. Iron rising as vapor where the stellar heat is strongest. Winds carrying it toward twilight. Droplets forming where the air cools just enough to let metal fall. And because science is careful, the image remains alive rather than frozen. Future observations may refine the temperatures, the wind speeds, the vertical structure, the exact condensation pathways, and the role of other metals and molecules. The phrase "iron rain" is not an ending. It is a doorway into atmospheric physics under conditions that once existed only inside equations. WASP-76b is bizarre because it takes the familiar poetry of rain and rebuilds it from elements we associate with anvils, cores, and molten industry. It reminds us that weather is not defined by water, but by the movement of matter through changing temperature and pressure. Wherever a substance can evaporate, travel, cool, and condense, some form of weather may be born. On Earth, that substance is water. On other worlds, it may be silicate, salt, carbon compounds, or metal. And on WASP-76b, beneath a star that never sets, on one side of the planet, the sky may carry vaporized iron into darkness, where the night receives it in a rain no living ear will ever hear, falling silently through the deep atmosphere of a world too hot, too strange, and too beautiful to fit inside the small weather of home. If WASP-76b teaches us that weather can become metallic, Celt 9b takes us one step closer to the edge where the word planet begins to tremble. Because this is not merely a hot world, not merely a gas giant basking too close to its star, but an atmosphere pushed into a state where ordinary chemistry itself becomes unstable, where molecules are torn apart by heat on the day side and may only begin to reform after being carried into darkness. To understand why KELT 9b feels so extreme, it helps to remember that Jupiter, the great gas giant of our own solar system, lives far from the sun, cold in its upper clouds, immense and storm-banded, shaped by internal heat, rotation, and deep atmospheric layers rather than direct stellar punishment. KELT 9b is also a gas giant, but it belongs to the class known as ultra-hot Jupiters, planets similar in broad category to Jupiter, but orbiting so close to intensely luminous stars that their atmospheres become laboratories of high-temperature physics. KELT 9b orbits its star in about 1.5 Earth days at a distance of only a few hundredths of an astronomical unit, and its host star is not a calm, sun-like object. KELT 9 is a hot A-type star, much hotter and more massive than the Sun, pouring out intense ultraviolet radiation that changes the rules of the planet's atmosphere. A close-in gas giant around a cooler star can already be exotic. A close-in gas giant around a star like KELT 9 becomes almost transitional, not because it is turning into a star, but because the environment around it begins to resemble conditions where molecular bonds cannot survive. On the day side, temperatures reach thousands of degrees, high enough that molecular hydrogen, H2, can be dissociated into separate hydrogen atoms. This process is not a metaphor. A molecule is held together by electromagnetic bonds, and when the surrounding gas absorbs enough energy through radiation and collisions, those bonds can be broken. The day side of KELT 9b receives so much energy that hydrogen molecules may be ripped apart, and when atmospheric circulation carries that atomic hydrogen toward the night side, the cooler conditions can allow some atoms to recombine into molecules, releasing heat in the process. This creates a powerful atmospheric cycle that has no close equivalent on Earth. Dissociation absorbs energy on the day side, recombination releases energy on the night side, and the planet's heat transport is shaped not only by winds, but by the making and unmaking of chemical bonds. In simpler hot Jupiter models, scientists often begin with stellar irradiation, pressure, temperature, opacity, and wind patterns, asking how energy moves from the day hemisphere to the night hemisphere. But for ultra-hot Jupiters like KELT 9b, hydrogen dissociation and recombination become part of the climate engine. The atmosphere is not just carrying heat, it is storing and releasing energy through chemistry that changes as air moves around the planet. This is one reason KELT 9b is so important scientifically. It forces exoplanet models to move beyond the comfortable language of averaged temperature and into a regime where radiative transfer, hydrodynamics, chemical equilibrium, non-equilibrium processes, ionization, and escape must all be considered together. The intense heat also means that many molecules that might dominate cooler giant planets cannot remain stable on the day side. Water vapor, methane, ammonia, titanium oxide, and other species may be destroyed, suppressed, or present only under certain pressure-temperature conditions. Metals that would normally condense into clouds or remain hidden in deeper layers can appear in atomic or ionized form. Observations have detected species such as iron and titanium in the atmosphere of KELT 9b, helping establish it as one of the defining examples of the ultra-hot Jupiter class. This is an atmosphere where elements behave more like a thin stellar boundary than like the cloud tops of a familiar planet. Even the idea of clouds becomes complicated, because at such temperatures, many condensates cannot form where the day side is hottest. A clearer atmosphere may allow radiation to penetrate differently, while ionized metals can absorb strongly at particular wavelengths, shaping the observed spectrum in ways that require detailed, high-resolution analysis. During a transit, as Kelt 9b crosses the face of its star, the starlight filters through the planet's extended atmosphere, and spectral lines appear or shift depending on what atoms are present and how they move. These lines can reveal atmospheric winds, orbital motion, and the presence of escaping gas. Because the planet is so strongly irradiated, its upper atmosphere is expected to be inflated, heated, and perhaps escaping into space. Atmospheric escape is a natural consequence when high-energy radiation deposits energy in the upper layers of a planet, increasing the speed of particles and allowing some gas to overcome gravity. On a giant planet, gravity is strong, but close-in irradiation can be relentless, and observations have found evidence for an extended hydrogen envelope around Kelt 9b. The planet may be losing mass, though the exact long-term fate depends on the escape rate, the planet's internal structure, stellar evolution, and the timescale over which the host star changes. It is tempting to say the planet is doomed, and in a broad evolutionary sense, it may be, especially because massive hot stars live shorter lives and expand as they evolve. But the careful phrasing matters. Astronomy often deals in probabilities, not melodrama. KELT 9b is enduring now in a temporary but real state. And temporary states are often the most informative. They show us processes in motion. The planet is not simply a catalog entry. It is an atmospheric experiment being performed by nature at a scale no laboratory on Earth could reproduce. Its day side teaches us what happens when gas giant chemistry approaches stellar temperatures. Its night side teaches us how circulation redistributes energy under extreme irradiation. Its escaping hydrogen teaches us how close-in planets can be eroded by their stars. Its metal lines teach us how high-resolution spectroscopy can turn a faint atmospheric signature into a map of physical conditions. The history behind this discovery also reveals how exoplanet science has matured. Early planet discoveries around sun-like stars were often defined mainly by mass and orbit, enough to show that hot Jupiters existed, and that planetary systems could be arranged in ways our solar system did not predict. Later, with space telescopes and high-resolution spectrographs, the field began moving from detection to characterization. It was no longer enough to know that a planet was there. Scientists wanted to know what its atmosphere contained, how heat moved across it, whether clouds formed, whether gas escaped, and how the star shaped the planet over time. Kelt 9b sits at the far end of that progression, a world so extreme that the star does not merely illuminate it, the star chemically edits it. Every moment on the day side, radiation pours into the upper atmosphere, breaking molecular bonds, ionizing atoms, swelling gas outward. Winds then carry some of that altered material around the globe, where the relative darkness allows partial recombination and cooling, though the night side is still far beyond any habitable imagination. The planet may be tidally locked, so its face toward the star remains fixed, a permanent hemisphere of glare, while the far side receives only transported heat and the faint memory of broken molecules being made whole again. This division creates a strange planetary rhythm without sunrise, a chemical pulse around a world that circles its star in less than 2 Earth days. And if we step back, the true strangeness becomes larger than temperature alone. Celt 9b is bizarre because it shows that a planet's identity is not sealed by formation. A gas giant placed far from a star becomes one kind of world. A gas giant placed close to a mild star becomes another. A gas giant placed next to an extremely hot star becomes something else again. A world where the atmosphere is expanded, stripped, dissociated, ionized, and lit from within by physics that feels almost stellar. The planet is still a planet by mass and by its orbit around a star, but its atmospheric behavior belongs to a frontier zone. It stands between the familiar and the nearly unrecognizable, reminding us that categories in astronomy are useful, but nature is continuous. Somewhere in the night, KELT 9b keeps racing around its brilliant star, completing year after year in a rhythm faster than human sleep, its day side too hot for molecules to remain themselves, its night side receiving the fragments carried by winds, its upper atmosphere reaching outward, as if the planet were slowly exhaling into space. And in that harsh, luminous exhalation, there is a quiet lesson for anyone listening in the dark. The universe does not merely build worlds. It tests them, reshapes them, and sometimes places them so close to fire that even chemistry must learn how to break apart and begin again. At first, the idea sounds almost wrong, as if the universe has made a quiet mistake. A planet larger than the star it orbits? We are so used to the architecture of our own solar system that the hierarchy feels obvious, almost moral in its order, with the sun vast and commanding at the center, and the planets smaller, cooler, and obedient in their long paths around it. Jupiter may be enormous compared with Earth, large enough to hold more than 1,000 Earths by volume, yet beside the sun it becomes modest, a striped marble circling a sphere so wide that more than 100 Jupiters could be placed across its diameter if nature allowed such a clean comparison. But once we leave the solar system, size begins to separate from power, and the old intuition starts to loosen. A star is not defined by being visually huge. A star is defined by mass, by the physics of its interior, by whether pressure and temperature in its core can support nuclear fusion, or once did in the case of stellar remnants. A planet, likewise, is not always small in radius simply because it is low in mass. Gas giants can be inflated, young, hot, and spread out, while dead stars can be compact, dense, and astonishingly small. This is the first key to the paradox. Mass and radius are not the same story. A neutron star can contain more mass than the Sun inside a sphere only about the size of a city. A white dwarf can hold a large fraction of a star's mass inside a body roughly Earth-sized. A gas giant, meanwhile, can have far less mass but a much larger radius because its matter is not crushed to the same extreme density. So when we ask whether a planet can be larger than its parent star, we must ask larger in what sense? larger by mass would not make sense in the ordinary planet-star relationship, because the more massive object governs the system and may cross into stellar or brown dwarf physics. Larger by volume or radius, however, is not only possible. In some systems, it has already become one of the most haunting demonstrations of how strange planetary architecture can be. WD 1856 plus 534b is one of the clearest examples to hold in the mind. It is a giant planet candidate, roughly Jupiter-sized, orbiting a white dwarf. The exposed core left behind after a sun-like star exhausted its central fuel, expanded into a red giant, shed its outer layers, and settled into a slowly cooling stellar remnant. The white dwarf is small, only around the scale of Earth, while the planet is about the scale of Jupiter, making the planet far wider than the star it circles. If you imagine the system visually, the usual picture reverses. The star is not a golden furnace filling the sky of space with size, but a pale, compact ember, dense and ancient, while the planet is the broad, dark giant moving around it every day and a half. Yet the deeper mystery is not only that the planet is larger, it is that it is there at all. A white dwarf was once the core of a star that passed through a red giant phase, and during that phase, the star's outer atmosphere would have expanded enormously, likely engulfing or destabilizing any close-in planets. WD 1856 plus 534b now orbits very close to the remnant, so it probably did not sit peacefully at that location through the entire stellar death process. A more plausible pathway is that the planet once lived farther out, survived the violent transformation of its star, and was later driven inward by gravitational interactions, perhaps involving other planets or stellar companions, before tides circularized its orbit near the white dwarf. This is not a simple fairy tale of survival. It is an orbital crime scene. The present system is evidence of a past rearrangement, a history written in where the planet is now compared with where it could safely have been before. The mathematics behind such migration can involve high eccentricity pathways, where a distant planet is perturbed into a stretched orbit that brings it close to the white dwarf at periastron, and over many passages, tidal dissipation removes orbital energy until the path becomes tighter and more circular. In that process, angular momentum, tidal quality factors, companion masses, eccentricities, and timescales all matter, and the system becomes less like a static picture and more like a long gravitational memory. This is why planets around white dwarfs are so valuable. They show not only what planets can be, but what planets can endure after their stars have changed beyond recognition. They also remind us that our solar system has a future. Billions of years from now, the sun will also become a red giant and then a white dwarf. And although the exact fate of each planet depends on complex solar evolution and orbital dynamics, the study of white dwarf planetary systems gives us a distant mirror of what planetary survival may look like after the warm main sequence chapter ends. From there, the question widens into another one. How large can a planet become before it is no longer clearly a planet? This sounds like it should have a neat boundary, but nature prefers gradients. If an object grows massive enough, its interior pressure and temperature may allow deuterium fusion, a limited form of nuclear burning often associated with brown dwarfs rather than planets. A commonly used dividing line is around 13 Jupiter masses, but that boundary is not perfect because formation history matters too. A body slightly below that mass might form like a star through direct collapse of a cloud fragment, while a body near or above it might form in a disk around a star like an enormous planet. Radius adds another complication. Gas giants do not simply get larger forever as they gain mass. Up to a point, adding gas can increase radius, especially for young or highly irradiated planets with extended atmospheres. But beyond a certain range, gravity compresses the interior more strongly, and extra mass may make the object denser rather than much wider. This is why Jupiter, brown dwarfs, and even very low-mass stars can have surprisingly similar radii despite very different masses. The physics is governed by pressure support, electron degeneracy, thermal history, composition, irradiation, and age. A young giant planet may appear bloated because it still retains heat from formation. A hot Jupiter close to its star may become inflated through mechanisms still studied, including stellar irradiation, ohmic dissipation, tidal heating, delayed cooling, or atmospheric circulation effects. A directly imaged object embedded in dusty material may appear larger or brighter than the solid planetary body itself because surrounding gas, dust, or a circumplanetary disk contributes to the observed light. That is why claims about the largest exoplanet must be handled with care. Some catalogued objects have enormous estimated radii, but the measurement may be influenced by youth, heat, model uncertainty, or extended material around the companion. HD 100546b, for example, is often discussed as a very large gas giant candidate in a young system. But young, directly imaged planets are difficult because they glow from their own heat and may be entangled with the environment where moons or disks are still forming. The boundary between planet, brown dwarf, and substellar companion becomes especially soft in these cases. Instead of imagining a ruler placed against a clean sphere, it is better to imagine astronomers reconstructing a faint, warm object from infrared light. Evolutionary models, distance, age estimates, and the behavior of nearby dust. Each measurement narrows the possibilities, but does not always close them. The most honest answer to how big planets can get is therefore layered. A mature gas giant made mostly of hydrogen and helium will rarely grow far beyond a few Jupiter radii before gravity and internal compression resist further expansion. Some young or highly inflated planets may appear much larger, especially if they are hot, low density, or surrounded by extended material. Around compact stellar remnants, a normal Jupiter-sized planet can be larger than its star by radius, even while the star remains vastly more massive and physically dominant. And at the upper edge of mass, the concept of planet merges into brown dwarf territory, where deuterium burning, formation pathway, and observational uncertainty all complicate the label. This is what makes the question so beautiful at night. It does not reduce to a single champion with a crown. It opens into the deeper structure of astrophysics. Mass against radius, heat against gravity, youth against cooling, formation against classification, survival against stellar death. A planet larger than its star is not a violation of cosmic order. It is cosmic order seen after our simple childhood diagram has been folded away. Somewhere in the dark, a Jupiter-sized world circles a dead white ember. Its star small but dense, its orbit close and strangely preserved, its existence whispering that planets are not always minor ornaments around blazing suns. Sometimes the star becomes the small thing, the planet becomes the wide shadow, and the system becomes a quiet reminder that in astronomy, size is never the whole truth, and the universe is most strange when it teaches us to separate what looks large from what truly holds the weight of gravity. Saturn has always been the quiet monarch of rings in the human imagination. A pale golden world surrounded by a thin, luminous architecture of ice and dust, so delicate through a telescope that it feels less like a physical structure than a thought drawn around a planet by gravity itself. And for a long time, it seemed almost impossible that nature could make anything more graceful, more enormous, or more strange. But then, in the archived light of a young star called J1407, astronomers found a dimming event so deep, so long, and so complicated that Saturn suddenly felt like only the small local version of a much larger idea. The event happened in 2007, though its meaning was recognized later, when data from automated sky surveys revealed that the star 1SWASPJ140747.93 minus 394542.6, often shortened to J1407 or V1400 Centauri, had faded in a way ordinary planet transits could not easily explain. A typical gas giant passing in front of a star may block a small fraction of the light, perhaps 1% if the geometry is favorable, and the transit curve usually has a smooth shape. Brightness dips, remains lower for a time, then rises again. But the J1407 event lasted for roughly 56 days and contained a complex sequence of deep, structured eclipses, like a shadow made not by one dark sphere, but by many bands of material moving across the star. At its deepest, the star's light was blocked by an extraordinary amount, suggesting that whatever passed in front of it was not merely a planet-sized body, but something surrounded by a vast disk or ring system. The proposed companion became known as J1407b, and the popular imagination quickly called it a kind of super Saturn. But the more careful scientific description is more interesting than the nickname. It may be a massive planet or brown dwarf candidate with a giant circumplanetary disk, possibly a young ring system in the process of becoming moons. That distinction matters because when we talk about rings on a mature planet like Saturn, we usually imagine a stable, elegant arrangement of small particles orbiting within the planet's gravitational influence, shaped by collisions, resonances, moons, and the Roche limit. the region where tidal forces can prevent loose material from assembling into a single large moon. But around a young giant object, rings may not simply be decorative remnants. They may be construction material. A circumplanetary disk is the smaller cousin of a protoplanetary disk, a rotating storehouse of gas, ice, dust, and rock around a forming planet or substellar companion. And, inside such a disk, moons may grow the way planets grow around a star. The J1407 light curve was interpreted with a model containing dozens of rings, about 37 in one influential reconstruction, extending to a radius of roughly 0.6 astronomical units, or around 90 million kilometers, an almost unsettling scale for something described with the same word we use for Saturn's rings. To feel that number properly, you have to slow down with it. Saturn's main ring system stretches hundreds of thousands of kilometers, already immense by human standards. But the proposed J1407 structure reaches outward on the scale of inner planetary orbits, approaching distances that make it feel less like a ring system and more like a miniature solar system wrapped around an unseen companion. If such a structure were placed around Saturn in our own sky, it would dominate the night with a size no ordinary moon could match. Not a small halo, but a vast, luminous bandwork stretching across the heavens. Yet, the beauty of the image is balanced by caution. J1407b has not been cleanly confirmed as a normal orbiting exoplanet with a settled ring system, and no repeat eclipse of the same kind has been observed, which is a serious problem if the object has a predictable orbital period around the star. Historical photographic plates and later surveys have not produced a simple recurring pattern. Some orbital solutions have been ruled out, especially circular orbits that would have brought the companion back into view in a regular way. To preserve a ringed companion explanation, models have to explore more complicated paths, such as a highly eccentric orbit and a ring system rotating in a retrograde direction relative to the companion's orbit around the star. Because prograde rings filling a large fraction of the Hill sphere may be disrupted too easily by stellar tides during close approaches. The Hill sphere is the region around a planet or companion where its gravity dominates over the star's gravity strongly enough to retain orbiting material. And for an enormous ring system, that boundary becomes crucial. Rings cannot extend indefinitely. If they reach too far, the star begins to interfere, stripping or destabilizing material. This means the proposed J1407 rings are not only large, they sit near a fascinating dynamical limit, where the companion's gravity, the star's gravity, orbital eccentricity, and the direction of particle motion all decide whether the structure can survive. In this sense, J1407b is less like a confirmed portrait and more like a difficult equation written in starlight. The light curve is the clue. The rings are one possible translation. Other interpretations remain possible, including the idea that the eclipsing object was not bound to the star in the expected way, perhaps a free-floating or passing substellar object with its own disk that happened to cross our line of sight. That possibility sounds improbable at first, but astronomy is often a science of rare alignments, and the absence of a repeat event forces humility. What makes the case so compelling is that the dimming was not random. The structure in the light curve contained gaps and changes that can be modeled as rings of varying opacity, and one gap around 0.4 astronomical units in the model has been discussed as a possible sign of an exomoon carving out material, much as moons in Saturn's rings sculpt gaps and edges through gravitational resonance. If that interpretation is right, then the J1407 event may not have shown us a ring system in the quiet old sense, but a moon-forming disk caught during a transitional phase. A place where particles were beginning to organize into satellites. This is where the story becomes deeper than spectacle. Rings are not just pretty circles. They are records of angular momentum, collisions, tidal boundaries, material strength, and time. In a young disk, small particles collide and either stick, fragment, or drift. Gas drag can move solids inward or outward. Embedded moons can open gaps by exchanging angular momentum with nearby particles. Resonances can gather material into edges, waves, and separations. The architecture of the disk becomes a visible consequence of invisible mechanics. When astronomers model a ringed eclipse, they are not only asking how wide the rings are, they are asking how opaque each region is, how fast the structure moved across the star, how large the star appears relative to the ring pattern, what inclination the disk had, and whether the inferred material can remain gravitationally bound. Each dip in brightness becomes a narrow shadow cast by a different part of the system, and the entire event becomes a slow scan across a cosmic disk too distant to resolve directly. There is a tenderness in that method, because the telescope never saw rings the way an artist paints them. It saw the star vanish and return in pieces. It saw absence arranged into structure. From that absence, scientists built a possible world. And perhaps that is why J1407b continues to hold attention, even with all the uncertainty around it. Confirmed planets can be strange, but unconfirmed possibilities can be strangely powerful when they reveal what nature might be capable of and what our data still cannot decide. J1407b sits at the border between discovery and mystery, between a planet, a brown dwarf, a circumplanetary disk, a ring system, and perhaps a moon nursery. If it exists as originally imagined, it would be one of the most visually astonishing planetary systems ever inferred. A giant companion surrounded by rings so broad they resemble a system of worlds waiting to form. If the original interpretation is wrong, the event is still valuable, because something caused that star to dim in a complex and extraordinary way. And whatever that something was, it belongs to the same deeper question. How does material gather, orbit, flatten, collide, and become organized under gravity? Saturn shows us the mature poetry of rings. J1407 may show us their wild youth, or the shadow of something even harder to classify. Either way, the lesson is quiet and immense. Around planets, as around stars, disks are temporary pages in the long story of formation. They may shine for a while as rings, thicken into moons, thin into dust, or disappear into darkness. And somewhere beyond our direct sight, perhaps around J1407 or around another young giant still hidden in the catalogs of the sky, there may be a world wearing a ring system so vast that it feels less like jewelry and more like an unfinished solar system, turning slowly in the dark, building moons from shadow, dust, and time. There is a certain comfort in imagining rocky planets as solid things, as worlds with ground, crust, mountains, basins, and some patient boundary between the sky above and the stone below. Because Earth has taught us that rock is the quiet part of a planet, the thing that holds still while oceans move, winds travel, clouds gather, and life walks softly across the surface. But 55 Cancri E asks us to loosen that instinct, because here the rock may not be still at all. This planet, also known as Janssen, is a super-Earth orbiting the star 55 Cancri so closely that one full year lasts only about 18 hours. Not long enough for an Earth day to finish before this distant world has already circled its star and begun again. It is larger and more massive than Earth, roughly in the range where astronomers use the term super-Earth, but that name can be misleading if heard too gently. Super-Earth does not mean a better Earth, or a more habitable Earth, or a world with deeper forests and wider oceans. It simply means a planet with more mass than our own, but less than the ice giants of the outer solar system, a category common in the galaxy, yet absent from our local family of planets. The solar system has small rocky worlds like Mercury, Venus, Earth, and Mars, then a wide jump to Uranus and Neptune. But between those sizes, the galaxy seems to have built many worlds, and 55 Cancri E is one of the most dramatic examples of what can happen when such a planet is placed almost against the fire. Its orbit is only about 0.015 astronomical units from its star, so close that the star would dominate the sky with a size and intensity that no earthly sunrise could prepare us for. Under that radiation, a rocky surface does not behave like the crust beneath our feet. At high enough temperature, minerals soften, melt, evaporate, and interact with whatever atmosphere survives. The surface may include a magma ocean, not in the mythic sense of a Red Sea painted for drama, but in the physical sense of silicate rock held in a molten state by constant stellar heating. On Earth, magma is mostly hidden below the crust, rising only where tectonics, mantle plumes, or fractures allow it to reach the surface. On a lava planet, the relationship may be reversed. The molten state may not be a local eruption, it may be the climate. If 55 Cancri E is tidally locked, as close-in planets often are, then one hemisphere may face the star continuously while the other remains turned away, creating a permanent day side of intense heating and a night side shaped by transported heat, interior flow, and whatever atmosphere or vapor circulates around the globe. The word ocean becomes strange here, because a magma ocean is not water. It is molten rock, a liquid made from materials we usually think of as mountains, mantle, basalt, feldspar, pyroxene, and silicate structure. It would be dense, glowing, and chemically active, and unlike a quiet sea reflecting moonlight, it would be part of the planet's deep interior, exposed to the sky. This makes 55 Cancri E scientifically powerful because it may show us a state that rocky planets pass through during their youth. The early Earth, the early Moon, and other young terrestrial bodies likely experienced magma ocean phases after giant impacts or intense accretional heating. But those stages vanished billions of years ago, leaving only geochemical traces in rocks. A lava world around another star can act as a living analog of that ancient condition, not because it is identical to early Earth, but because it allows us to study the physics of molten rocky planets while the process is still happening. The basic measurements tell only the beginning of the story. From the transit, astronomers measure how much light the planet blocks, giving a radius. From radial velocity, they measure how the planet's gravity tugs the star, giving a mass. From mass and radius together, they infer an average density. And from density, they begin to constrain possible interiors. But an average density is a deeply compressed clue. It can hide many combinations of iron core, silicate mantle, volatile envelope, carbon-rich material, or lower density layers. Early speculation famously suggested that 55 Cancri E might be rich in carbon, perhaps even containing diamond-like material under enormous pressure. Though later work has made the composition less simple and more cautious. That history matters because it shows how exoplanet science grows. A first model catches the imagination. Then, better stellar abundances, better radii, better masses, better atmospheres, and better thermal observations refine the picture. The planet becomes less like a headline and more like an evolving argument between data and physics. One of the most important changes came from thermal observations. If the planet had no atmosphere at all, the day side would be extremely hot and the night side might be much cooler because bare rock does not redistribute heat very efficiently around a tidally locked planet. If an atmosphere exists, especially one rich in gases such as carbon monoxide or carbon dioxide, it could carry heat from the day side toward the night side, reducing the contrast and changing the shape of the planet's phase curve, the variation in infrared brightness as different hemispheres come into view. Webb observations have strengthened the possibility that 55 Cancri E may have atmospheric gases, perhaps a secondary atmosphere generated by outgassing from the molten surface, rather than a primordial atmosphere preserved from formation. This distinction is essential. A close-in rocky planet, so near its star, may have lost an original atmosphere under intense radiation and stellar wind. But if its interior remains molten and volatile bearing, it could continuously release gases from below, rebuilding a temporary atmosphere that is destroyed, replenished, and altered over time. In this way, the boundary between geology and meteorology almost disappears. On Earth, volcanoes contribute gases to the atmosphere, but the atmosphere has many sources and long-term reservoirs. On 55 Cancri E, the molten surface itself may be the atmospheric source, the ground breathing upward into the sky. The chemistry of that sky would depend on temperature, pressure, oxygen fugacity, interior composition, stellar irradiation, and the equilibrium or non-equilibrium reactions between magma and gas. Carbon monoxide, carbon dioxide, water vapor, sulfur-bearing species, sodium, potassium, or silicate vapor could all be relevant under different assumptions, though the exact mixture remains a subject of active research rather than a settled portrait. The phrase sparkling skies is sometimes used for this world because under some models, mineral vapors or condensates could form clouds or droplets from materials that would be solid rock on Earth. But again, the beauty must be held with precision. These would not be gentle clouds drifting over a blue ocean. They would be the atmospheric expression of a planet whose surface and air are chemically connected by heat fierce enough to make stone participate in weather. This is what makes 55 Cancri E so bizarre in a deeper sense. It does not merely have lava. It may have a lava atmosphere system. The surface may evaporate into the air may radiate into space, stellar light may break molecules apart, and the interior may keep supplying new gases, producing a planetary state that is dynamic rather than stable. Even the interior flow could be unlike Earth's mantle convection. A permanent dayside magna ocean could focus heat and buoyant material under the substellar point, while cooler regions near the night side might allow thicker crust or different circulation patterns. The planet's deep mantle, if partly solid, may respond to asymmetric surface temperatures, producing internal circulation linked to the external climate. That is a profound reversal of how we usually imagine planets. Not a separate inside and outside, but a coupled body where the star-facing surface, molten mantle, atmosphere, and radiation field all talk to one another through physics. And because 55 Cancri E is close to a bright nearby star by astronomical standards, it is one of the few rocky exoplanets where this conversation can actually be tested. Each eclipse, when the planet passes behind the star, lets astronomers subtract the star's light and estimate the planet's dayside emission. Each phase curve gives hints about heat transport. Each spectrum searches for gases that might survive above molten rock. The world itself is unreachable, but its glow arrives in our telescopes after crossing about 41 light years, carrying faint information from a surface that may be oceanic, not with water, but with stone. It is easy to call such a planet hellish, and in human terms, that is fair. No life as we know it could rest on a surface where rock melts and the year is shorter than a day. But scientifically, 55 Cancri E is not just a nightmare. It is a rare, exposed chapter of rocky planet evolution. It lets us ask how terrestrial planets lose atmospheres, how they regenerate them, how magma and gas exchange elements, how super-Earth interiors behave under stronger gravity, and how far the word Earth-like can stretch before it breaks. In the quiet dark of this journey, 55 Cancri E becomes a reminder that rock is not always patient, ground is not always ground, and oceans are not always made of water. Somewhere near the star 55 Cancri, a world heavier than Earth circles in less than a day, its star hanging enormous over one hemisphere, its surface perhaps glowing in molten tides of silicate, its atmosphere, if present, rising like breath from magma, changing as fast as radiation, chemistry, and interior heat allow. And in that fierce, silent orbit, the universe shows us that a rocky planet can become something almost fluid, almost atmospheric, almost alive in its geology. Not a home like Earth, but a memory of what young rocky worlds may once have been, when their surfaces were still molten and the boundary between planet and fire had not yet fully cooled. Not every bizarre planet announces itself with fire, iron rain, or a ring system large enough to feel like a small solar system. Some of the strangest worlds in the galaxy are strange because they refuse to become clear. Because every time we try to place them into one of our familiar categories, they soften at the edges, hidden under haze, pressure, hydrogen, possible oceans, deep atmospheres, and the quiet limits of what starlight can tell us. K218b and GJ1214b belong to this more subtle kind of mystery. They are not tiny rocky worlds like Earth, and they are not full ice giants like Neptune, at least not in the simple way our solar system taught us to think. They occupy the broad and crowded territory often called sub-Neptunes or mini-Neptunes, planets larger than Earth but smaller than Neptune, a class that appears to be extremely common around other stars and yet is missing from our own planetary family. That absence matters more than it first seems. Our instincts were trained by local examples: Mercury, Venus, Earth, and Mars as rocky planets, Jupiter and Saturn as gas giants, Uranus and Neptune as ice giants wrapped in thick envelopes. But the galaxy seems to have filled the gap between Earth and Neptune with countless intermediate worlds. And because we do not have one nearby to fly past, orbit, drill, sample, or watch with a spacecraft, every sub-Neptune becomes a kind of locked room. We know its mass, sometimes its radius, sometimes its orbital period, sometimes a few molecular fingerprints in its atmosphere, but the interior remains hidden. A planet with 2 or 3 Earth radii could be a rocky core with a thin but extended hydrogen envelope, a water-rich world with high-pressure ice layers, a mini-Neptune with a deep atmosphere and no accessible surface, or something more complex that does not match any single label. This is why K218b drew such intense attention. It is about 8.6 times Earth's mass, orbiting within the habitable zone of a cool red dwarf star. And Webb observations have found carbon-bearing molecules such as methane and carbon dioxide in its atmosphere. Those detections are important because they suggest that small, temperate planets with thick atmospheres can now be studied chemically across interstellar distance. But the interpretation is delicate. Some models propose that K218b could be a Hacean world, meaning a planet with a hydrogen-rich atmosphere over a global ocean, a kind of environment unlike Earth, but perhaps not automatically hostile to all chemistry of interest. Other models argue that it may instead be a more typical sub-Neptune with a deep atmosphere, high pressures, and conditions that do not require a habitable ocean at all. The word habitable zone can mislead if we let it become too warm in the imagination. It only means that, under certain atmospheric assumptions, the amount of starlight could allow liquid water somewhere. It does not guarantee a surface, an ocean, a stable climate, or life. Around a red dwarf, the story becomes even more layered because stellar activity, flares, atmospheric escape, tidal effects, and long-term orbital evolution can all reshape planetary conditions. K218b is therefore not a promised second Earth. It is a test case for how carefully we can read a world that is both promising and ambiguous. The discussion around possible dimethyl sulfide, or DMS, and dimethyl disulfide, or DMDS, shows how science should sound when the stakes are high. On Earth, DMS is associated with biological sources, especially marine microorganisms, so any possible detection in an exoplanet atmosphere naturally draws attention. But attention is not confirmation. Spectral features can overlap. Different molecules can absorb light at similar wavelengths. Instrument reductions, noise, cloud structure, atmospheric temperature profiles, and model choices can change how strong a claimed signal appears. Some analyses have found possible hints. Other joint analyses of Webb data have argued that the evidence is not statistically strong enough to support a confident detection. That tension is not a failure of science. It is science protecting itself from wanting too much too quickly. A faint molecular feature in the atmosphere of a planet more than 100 light-years away must survive the hardest kind of questioning before it can become a reliable claim. K218b is bizarre then, not because we know it is alive, and not because we know it has an ocean, but because it sits exactly where our curiosity is most vulnerable. Large enough to hold an atmosphere, cool enough to invite speculation, chemically interesting enough to matter, and uncertain enough to demand humility. GJ1214b, in a different way, deepens the same lesson. It is closer, about 40 light-years away, and it became one of the classic examples of a sub-Neptune whose atmosphere resisted easy interpretation. For years, astronomers tried to observe starlight passing through its atmosphere during transits, hoping to see clear absorption features from molecules. But the spectrum appeared muted, almost flat, as if the planet were wrapped in clouds or haze. A flat transmission spectrum is not empty. It is a wall. It can mean that aerosols high in the atmosphere are blocking our view of deeper layers, scattering or absorbing light before it reaches the regions where stronger molecular fingerprints would appear. In this sense, haze is not just a visual decoration. It is an observational barrier and a chemical clue. Aerosols can form through photochemical reactions when stellar radiation breaks molecules apart and allows new compounds to assemble, sometimes creating complex particles that float high above the planet, much as Titan in our own solar system is wrapped in orange organic haze. But GJ1214b is not Titan, and it is not Neptune, and it is not Earth. Webb observations measuring the planet's thermal emission and phase behavior have suggested a steamy or hazy atmosphere and helped constrain how much heat moves around the planet, giving astronomers a new way to probe beyond the old, flat spectrum. This is the shift from simple detection to climate inference. When a planet passes in front of its star, we measure transmitted light. When it moves behind the star, we can measure the dayside glow that disappears. When it orbits through different phases, we can track changes in brightness that reveal whether heat is trapped on the dayside or redistributed by winds. Each method adds another thin layer of knowledge, and together they begin to turn a mysterious disk of numbers into a physical world. For sub-Neptunes, that physical world may be dominated by pressure regimes unfamiliar to us. If a hydrogen-rich envelope is deep, there may be no solid surface in the Earth-like sense, only a gradual transition into denser fluid layers. If water is abundant, it may exist not as a gentle ocean under an open sky, but as supercritical fluid or high-pressure ice beneath thick gas. If the atmosphere is metal-rich, meaning rich in elements heavier than hydrogen and helium, its opacity, chemistry, and thermal structure can differ greatly from a simple solar composition envelope. These possibilities make classification difficult because mass and radius alone cannot decide the answer. Two planets with the same radius can have very different interiors. One may be rocky with a modest atmosphere. Another may have a smaller core wrapped in thick gas. Another may contain a large water layer under pressure. This degeneracy is one of the great quiet problems of exoplanet science. Many interiors can produce the same outward measurements. To break the degeneracy, astronomers combine mass, radius, stellar composition, atmospheric spectra, thermal emission, orbital history, and population statistics. They ask how common each type should be, how planets lose atmospheres under stellar radiation, how cores accrete gas in disks, how migration changes orbits, and how radius distributions reveal the dividing line between stripped rocky cores and gas-rich sub-Neptunes. K218b and GJ1214b are therefore not merely two odd planets. They are representatives of a hidden majority, a class of worlds that may be common enough to define the galaxy's planetary landscape, yet strange enough that we still do not know what to call them with confidence. Their mystery is not empty. It is structured. It lives in spectra, in pressure-temperature profiles, in clouds that flatten molecular features, in methane and carbon dioxide detections that open one door while closing none, in haze layers that conceal lower atmospheres, in models that compete honestly because the data are still young. There is something almost restful about this kind of uncertainty when it is handled carefully. It does not shout. It asks us to listen more precisely. After worlds of molten rock and torn-apart chemistry, these misted sub-Neptunes slow the journey down and remind us that the strangest planets are not always the loudest. Some are strange because they are veiled, because they sit between categories, because they show us that the universe has built a kind of planet our solar system never kept. Somewhere around a dim red star, K218b turns under a sky whose molecules are still being debated. Somewhere closer, GJ1214b hides beneath haze, its deeper atmosphere resisting our gaze. And in their soft refusal to become simple, these worlds reveal one of the most important truths in modern astronomy. Discovery is not the moment mystery ends, but the moment mystery becomes precise enough to study. The strangest ending to a journey through bizarre exoplanets is not a world of molten rock, not a planet with iron rain, not even a giant hidden behind a ring system so wide it feels like a small unfinished solar system. The strangest ending is a planet orbiting a star that has already died. Because in that quiet contradiction, the universe seems to ask whether worlds can survive after the light that shaped them has been broken apart. We tend to think of planets as children of living stars, born in disks of gas and dust, warmed by steady radiation, held in long patience by gravity. And if the star changes, the planets change with it. But around PSRB 1257 plus 12, the story begins after catastrophe. This object is a pulsar, a rapidly rotating neutron star, the collapsed core left behind after a massive star ended its life in a supernova. A neutron star is not large in radius like the Sun. It is compact beyond ordinary imagination, packing more mass than the Sun into a sphere only about the size of a city. And because it spins with extreme regularity while emitting beams of radiation, it can appear to pulse from Earth like a lighthouse in deep space. The first confirmed exoplanets were not discovered around a warm, sun-like star, but around this kind of stellar remnant, a dead star whose radiation environment is so severe that the phrase planetary system feels almost ghostly. The planets of PSRB 1257 plus 12 were found through pulsar timing, one of the most elegant detection methods in astronomy. A pulsar's signals arrive with extraordinary regularity, and if the pulsar is being tugged by orbiting planets, those pulses arrive slightly early or slightly late, because the pulsar itself is wobbling around the system's center of mass. The planets do not need to transit, they do not need to shine. Their presence is written as tiny deviations in the beat of a dead star. There is something almost haunting in that method. A world is detected because it makes a stellar corpse keep imperfect time. The discovery forced astronomers to confront a question that still feels difficult. How can planets exist there at all? One possibility is survival, that some planetary material endured the violent death of the original star, though a supernova is so energetic that ordinary inner planets would face devastating radiation, shock, mass loss, and dynamical upheaval. Another possibility is second-generation formation, where debris left behind after the stellar explosion or after the disruption of a companion object settled into a disk and formed planets anew. A third possibility may involve captured or rearranged material in a complex system history. None of these pathways should be treated as a simple certainty for every pulsar planet, because each remnant system carries its own dynamical past. But the mere existence of such worlds means planet formation is not confined to the gentle youth of sun-like stars. It may also occur, under some circumstances, in the aftermath of death. That idea changes the emotional temperature of exoplanet science. Around an ordinary star, planets can feel like natural companions. Around a pulsar, they feel like survivors, ruins, or reborn structures assembled from wreckage. Their environments are not likely to be kind in any familiar sense. Pulsars emit high-energy radiation and particle winds, and any planet nearby would be exposed to conditions profoundly different from the sunlight Earth receives. A rocky surface under such radiation might be stripped, sterilized, altered, or protected only if buried beneath material or far enough away. And although science should avoid turning every harsh world into an absolute statement of impossibility, pulsar planets are not promising homes for life as we know it. Their value is different. They show that planets can exist in places where our old intuition would not have placed them. They widen the definition of a planetary system until it includes not only calm stellar nurseries, but the remnants of supernovae, the precision of radio pulses, and the strange gravity of matter compressed to nuclear density. White dwarf planets extend this same theme in a different key. A white dwarf is the remnant of a lower mass star, like the Sun will one day become after it expands into a red giant and sheds its outer layers, leaving behind a hot, dense core that slowly cools over immense time. WD 1856b, a Jupiter-sized planet candidate orbiting the white dwarf WD 1856 plus 534, is one of the most striking known examples because it circles this stellar cinder every 34 hours and is far larger in radius than the star it orbits. The visual reversal is powerful. The planet is wide and dark, the star small and dense, and yet the star still dominates gravitationally because mass, not size, rules the orbit. But once again, the deeper mystery is history. A planet sitting so close to a white dwarf probably could not have remained at that distance while the star expanded through its red giant phase, because the star's outer layers would have reached far beyond the present orbit. The planet likely formed farther away and migrated inward after the star became a white dwarf, perhaps through gravitational interactions with other bodies or with distant stellar companions, followed by tidal circularization. This makes WD 1856b less like a peaceful survivor and more like a record of late-stage orbital rearrangement. In systems like this, the planet is not simply orbiting a dead star. It is carrying evidence that planetary systems remain dynamically alive even after the main star has left the main sequence. Long after the bright middle age of a star has ended, planets can still scatter, migrate, fall inward, or be destroyed. Some white dwarfs show signs of metal pollution in their atmospheres, which is surprising because heavy elements should sink out of sight quickly in such dense stellar remnants. The usual interpretation is that asteroids, comets, or planetary fragments have been perturbed inward and torn apart, feeding rocky material onto the white dwarf. In that sense, dead stars can become forensic laboratories for studying the composition of rocky bodies that once orbited them. The calcium, iron, magnesium, silicon, and other elements in a white dwarf's spectrum may be the ashes of minor planets, the chemical ghosts of worlds that did not survive. So the last chapter of Bizarre Exoplanets is not only about individual objects, it is about planetary mortality. The galaxy does not merely form planets and leave them unchanged. It ages them. It irradiates them. It scatters them. It strips their atmospheres, melts their surfaces, breaks their moons, sends some into interstellar darkness, and allows others to circle the remains of stars whose living light has gone out. When we remember the worlds we have crossed in this journey, the pattern becomes clearer. Ultra-short period planets showed us years compressed into hours, where orbital mechanics folds celestial time into a human evening. Multi-sun planets showed us skies built around moving centers of mass, where daylight can belong to more than one star. Rogue planets showed us that a world can be torn from its system and still carry mass, heat, and history through the darkness between stars. WASP 76b showed us that weather can become metallic when temperature turns iron into vapor. KELT 9b showed us that chemistry can be torn open by stellar radiation, with molecules broken on the day side and remade in cooler darkness. WD 1856b. And the planets around pulsars showed us that planetary systems can persist, transform, or even be reborn after stellar death. J1407b, if its ring interpretation is correct, showed us how disks around young companions may resemble moon nurseries on scales that dwarf Saturn's elegance. 55 Cancri E showed us that rock can become ocean, atmosphere, and weather when a super-Earth is placed close enough to fire. K218b and GJ1214b showed us that some planets are bizarre not because they are loud, but because they are veiled, hovering between categories our solar system never taught us to name. Together, these worlds answer the question at the heart of the entire journey. The most bizarre exoplanets we have found are not bizarre as isolated curiosities. They are bizarre because each one reveals a different way the universe can make, reshape, conceal, and end a world. They teach that Earth is not the center of planetary possibility, nor even the best template for imagining what a planet can be. Earth is one outcome, temperate, ocean-bearing, chemically balanced in a rare and delicate way, orbiting a stable star at a distance that allowed life to write itself into the crust, the air, and the sea. But the galaxy contains outcomes that are molten, frozen, orphaned, irradiated, inflated, stripped, ringed, double-lit, chemically veiled, and bound to dead stars. The universe was never trying to resemble Earth. Earth was only the version of the universe that happened to become home. And as the night grows quieter, that thought can settle gently rather than frighten us. To learn about bizarre exoplanets is not to make Earth feel small in a cruel way, but to make reality feel wide. Each strange world is a sentence in a much larger language of gravity, heat, chemistry, time, and chance. Some sentences are bright, some are dark. Some are written in metal rain, some in molten stone, some in the pulse timing of a dead star. And somewhere beyond the reach of our current telescopes, countless pages remain unopened, waiting for a future shadow, a future spectrum, a future tremor of light to tell us that another impossible world has been there all along, quietly orbiting, drifting, glowing, or surviving in a universe that never needed to be familiar in order to be true. As we drift back from these distant worlds, remember that the universe is far stranger, deeper, and more creative than anything our solar system alone could teach us. If this journey brought you wonder or calm, please like, subscribe, and stay with us for more quiet explorations among the stars.